So we're into our last two sections of the pre-algebra course. I like to call these the smorgasbord topics because it's a little bit of everything. So realistically, I mean, the concepts in these sections are fairly straightforward, but you can actually combine some of these concepts into like more complicated application problems, which you'll probably see on the lab and the review sheet problems and things like that. But we'll just stick with the basics in these videos. So the three main things that are covered in these sections are right triangles and the Pythagorean theorem, volume of a rectangular solid, which is basically a box, and then the rectangular coordinate system. So we'll look at those three things in these two sections. So the first thing is just a review of square roots, which we looked at actually when we did sets of numbers back in the last unit. So remember, a square root of a number x is a number that needs to be multiplied by itself, in other words squared, in order to get x. So what does this mean mathematically? So mathematically this would mean a is a square root of x if a squared equals x. And the way we would write that is a equals radical x. And that's what we call the radical sign. And it indicates a square root. So we had said in that last unit that some numbers have square roots that are rational numbers while others resulted in irrational values. So examples that gave you rational numbers were just things like the square root of 16, because the square root of 16 equals 4. And the reason for that is because 4 squared equals 16, right? The square root of 144 was 12, and that was because 12 squared equals 144. And then if you take, like combinations of these numbers, like combinations of perfect squares, you can also get rational numbers, like things like the square root of 4 ninths. That was actually going to be 2/3. And that still works because if we do 2/3 squared, we get 4 ninths. Right? So those were all examples of square roots that gave you rational numbers. But then what if you had something like the square root of 2? Right? The square root of 2, on the calculator, it actually just gives us the square root of 2 because that's the only way you can write it in its exact form. If you want to get an approximation for the square root of 2, you had to change this calculator to what was called the classic mode. And once it's in the classic mode, now if I do the square root of 2, it's going to give me this crazy decimal, right? So the square root of 2 is not an exact value. It's just approximately 1.414 because it had no repeating pattern and it never ended. So this was what was called a irrational number, right? Whereas the other square roots were all perfect, so they were rational numbers. What's one situation where we end up using these square roots? Right triangles. Okay, because when we have a right triangle, and what is a right triangle? It's basically just a triangle that has one right angle, right? And a right angle is your 90-degree angle. So right there, that's your right angle there. That symbol is for the right angle. All right, so when you have a setup like this for a right triangle, A and B, right, the sides that form the right angle are known as the legs, and C, the side that's opposite the right angle, is called the hypotenuse. And then, of course, you have this famous relationship, which you remember, called the Pythagorean theorem, which says that the sum of the squares of the legs, right, so a squared plus b squared, is equal to the square of the hypotenuse. So what this does is this allows us then to find the third side of any right triangle as long as we know two of them. So suppose a equals 5 and b equals 12. Find c. Right? So what would we do? We would just use this Pythagorean theorem, right? So we know a squared plus b squared equals c squared, and we know that a is 5 and b is 12, so we substitute those. So order of operations would tell us to square first and then add. So this is 25, this is 144, and we square those and we get 169. And now if we know that c squared is 169, how would we find c? Well, we just use this idea of square roots that we looked at before. If we want to figure out what number squared gives us 169, we would just take the square root of both sides of the equation, which is a perfectly legal thing to do. You'll find that generally you can do a lot of things to equations as long as you do them to both sides, right? So one thing that we can legally do to an equation is take the square root of both sides. And when we take the square root of 169, we actually get 13. So if the two legs are 5 and 12, the hypotenuse would be 13. So that's what we just said there. So since the final step in using the Pythagorean theorem will be to take a square root, sometimes you'll end up with side lengths though that are irrational numbers. So then you can just approximate them if you need to. So like let's say, suppose a equals 4 and c equals 11. Find b, right? So again, we'd use a squared plus b squared equals c squared. In this case, a is 4 and c is 11. So now we have a little bit of a different setup, right? We're trying to solve for b, so we want to isolate the b. So we would still follow order of operations though, so we'd still square the 4 and the 11 first. But now instead of adding those together, we can't because they're not like terms. We're still trying to isolate the b. So what you'd have to do here is you'd subtract 16 on both sides, and then you'd end up with b squared equals 105. And now, to isolate, I would take the square root of both sides. So I would end up with that b is the square root of 105. But then I'd have to approximate this, right? So I could go to my calculator. It's going to be a little bit bigger than 10. So if I do the square root of 105, I have 10.25, let's say. So we'll say this is approximately 10.25. So when you get an irrational number like that, there's no way to tell what it is unless you punch it in the calculator to give an approximation. So b in this case is approximately 10.25. So our second little geometry topic in this section relates to the volume of a rectangular solid. And what is a rectangular solid? This might be like a box that you got a delivery in or something like that, right? So it would have a length, a width, and a height. And so remember that a volume is actually an amount of space inside a three-dimensional figure. So since it's three-dimensional, you're going to actually be measuring it in cubic units, right? So remember we had perimeter, which was one-dimensional because it was just the distance around the outside. We had area that was two-dimensional because it was the amount of space inside a figure, right? A two-dimensional figure. But now we have a three-dimensional figure, so the volume is going to be the amount of three-dimensional space inside a three-dimensional figure. So we have a box that has three dimensions, and we're going to be finding the volume. So let's suppose we have a box that we got a delivery in where you have these dimensions. All right, suppose a box measures 30 inches wide by 15 inches tall by 4 feet long. What is its volume? All right, well, the first thing that you should probably notice here is that the width and the height are given in inches and the length is given in feet. So we can't be mixing inches and feet. So we'd have to, convert either feet to inches or inches to feet. Now, personally, in this case, even though it might be tempting just to say 4 feet, what is it in inches? The problem with doing that is then you're going to be getting a huge number, right? Because you're going to be multiplying large numbers. So in this case, it's probably easier to convert 30 inches to feet and 15 inches to feet. So what you would do is you'd use our conversion factors that we had done in the last section, right? So we convert 30 inches to feet by multiplying by the conversion factor. 1 foot is 12 inches, and then we get our cancellation here. So then we'd just be doing 30 divided by 12, and 30 divided by 12 is actually going to be 2.5. So that's 2.5 feet, and then 15 inches, we use the same conversion factor, right? 1 foot is 12 inches, and we do 15 divided by 12, and 15 divided by 12 is going to be 1.25 feet. So this box is really 2.5 feet wide by 1.25 feet tall by 4 feet long. So now we can just use our V equals LWH formula, and we can plug in these values, right? So the length is 4, the width is 30 inches, which was 2.5 feet, and the height was 15 inches, which was 1.25 feet. So we're multiplying 4 times 2.5 times 1.25, so you end up with 12.5 cubic feet, which is the volume of this box. Right, now you might say, how did I get that so quick? I knew that 4 times 2.5 was just 10, and then when you multiply by 10, you're just moving the decimal over 1, so it's 12.5. So that wasn't really that tough of a calculation. So it's 12.5 cubic feet. Now, could you have done it the other way? Yeah, but again, the problem with doing it the other way with inches is you'd have to convert 4 feet into inches. So you would have done 4 feet. So then you'd have to flip the conversion factor. So it would be 1 foot on the bottom and 12 inches on the top. And now you would be multiplying instead of dividing. So 4 times 12 is 48. So then you'd be using these big numbers. So then you'd have the volume is 48 times 30 times 15. And 48 times 30 times 15 now is going to give you a huge value. So it's 21,600. So if you write it in cubic inches, it's 21,600 cubic inches. So it's a lot easier just to say it's 12.5 cubic feet. But I mean, either one would be acceptable unless they specifically tell you the units, right? They didn't tell me which units to use here, so I could have used either cubic feet or cubic inches. Either way it would work. But you definitely have to do some conversion before you're going to do that, right? Because you can't be mixing feet and inches in the same calculation.